All right, let's go. Hopefully this works. Yeah, Ron is in close to my time zone, right? Yeah, hello everyone. And yeah, so today I'm going to be working on something that I've talked about for quite a while now, which is a USB interface for, well, the original purpose is to be a serial cable for Apple M1 devices. But what it's actually going to be is a USB PD multi-tool of sorts and debug interface for different kinds of devices. And the reason for that is that basically it's not much more effort to do that versus it being strictly a serial cable for Macs. So I wanted to be a little bit more general than that. So so I've had this idea in my head for a while now, and I'll talk about what this, sort of what my plan is in a second. But first, just to go over how this all works, because I assume most people aren't familiar with USB Type-C. USB Type-C is an interesting standard. It's got a lot of pins, and as you know, it's reversible. And so the ones that we're most concerned with are basically these are the signals you get on a USB Type-C. You get two sets of high-speed. Can I do a area thing here? Yeah, you get two sets of high-speed signals, transmit and receive. You've got some grounds and variable power supply, and then you've got two sets, and many people don't know this, of USB 2.0 signals. But the cables only have one set. So most of the time you will think of a USB Type-C cable as having one set of USB 2.0 signals, and that would be correct, but the connector technically has two. And then there is a set of sideband use signals, SBU1 and SBU2. And then there's the actual cable control stuff. So that would be CC and VCon. And so you may have noticed that a lot of this is symmetric. So if you flip the connector around, the two sets of high-speed signals just swap places, and the USB 2.0 signals end up on the other side of the connector. SBU1 and SBU2 cross over, which is interesting, and CC and VCon switch around. And so this is how USB Type-C can tell which way you've plugged in, because CC and VCon are switched around. So the way it works is that on the device side, these two pins have to be interchangeable. And on the cable side, one CC line will be connected between both ends of the cable, and the VCon line will either not be connected or there's like a pull down or something. And so depending on which way you plug it in, the other ends can tell which side of is connected across to the other device via the CC line, and which side is just pulled down or VCon. And that way each side can tell which way the connector is plugged in on that side. So each side figures out which way the cable is flipped independently. And that's how you can figure out if the SBU pins are swapped and all that. So the interesting thing is that normally when you plug in a USB 3.0 device, it's just, the USB 2 pins give you the USB 2 bus, and then one of these USB 3 sets give you the USB 3 bus, or both if it's one of the high-speed modes that use both. Or you can end up with alternate modes where you can have DisplayPort over one of these sets, or DisplayPort over both of those sets, or Thunderbolt over both of those sets, and things like that. And so then when for fancier, Rod is talking about this right now, for fancier cables where the cable needs to identify itself to either end, what ends up happening is that this VCon signal is the power supply for this little chip in the cable for identifying itself, and the chip basically talks through CC. This is basically, CC is a bus, right? So both ends talk to each other, but if the cable has logic, then it can also talk through CC. And if the cable is even fancier and has repeaters, or is one of those Thunderbolt cables that has either equalization or redriving or all those different signal integrity improvements that they can have, or even if it's an optical cable that needs power to run the whole optical thing, then that will also come from VCon. And also for cables that can handle more power, also as Rod says, basically the default power capability of the cable on the VBus lines is up to 3 amps, if I'm not mistaken. Power supplies can be either USB. Well, with USB PD, it can be. It all gets very complicated. But the basic power levels for these things are the USB 2.0 level of 500 milliamps and 2 basic charging modes of 1.5 and 3 amps. And the cables are supposed to do up to 3 amps. But there are higher power modes that can go up to 5 amps. And then for those cables, they need to have the chip to tell the devices on either end that they can actually do 5 amps. So that's how this all works, and that's why you get all these complicated things where, like a cable can be like up to 100 watts, that means 5 amps, or a cable can be USB 2.0, which means it only has these pins in the middle and CC and almost nothing else, or it can be a full spec cable, which means it has all the pins except for this extra pair of USB 2 pins. So this is the only thing you don't get. So just to give you a bit of from the spec here, the standard type C. Yeah, so the standard cable will basically connect all the basically all the signals through. The high-speed pins just get basically crossed over, like transmit to receive, which makes sense, but not flipped over. The SPU 2 pins gets crossed over. There's only one set of USB 2 pins on the top side, which is like the side with the CC line. And then and then pretty much just power and VCon is not supposed to be connected through. And if it's one of the dumb USB 2.0 cables, then those really only have it's basically like an old school 4-pin USB 2 cable, except it also needs to have CC and the VCon stuff. And then there's the adapters for the old connectors. So these are the standard ones, right? So if you buy a USB Type-C cable, it's supposed to be either this or this. If you get anything else, it's weird and not standard. Or at least it should be compatible with these, right? So the VCon stuff, there was a diagram for this stuff somewhere in the spec that I forget, where it showed you the different states it can be in. I forget where this is. Is it here? VCon. I forget exactly where in the spec is. It's a little bit annoying to navigate. Give me a second, see if I can find that. I think it's here, maybe. Where was that? Ah, here, yeah. So basically, this is how it looks when you have a cable in between two devices, right? The CC line goes straight through, and then this VCon line is supposed to be pulled down, and so the host side basically has a pull up on both ends, and the device head has a pull down on both ends. And depending on the voltages you end up on these points, is how you can tell which side is connected to which end of the cable. And if you have an active cable, there is a thing with VCon, and I think there was another diagram with that, but I don't remember. Might not be here. But that's basically how it's supposed to work. Yeah. So here, if you have a VCon, this is how it's supposed to work, right? You have basically there's supposed to be a diode on either end, so either side can power the cable functionality. So basically, so this is just the background on how all this works. Now, here's what I want to build. First of all, let me think about how I want to. I guess I can just open the text editor, and I probably want to open a new session, something like that. Yeah. So, okay. The first goal is to be able to get a serial port working on these Macs. And so for that, you need these things. The serial port, so these Macs, like almost every USB Type-C device that is, like a computer or a fancy phone or something that has, a lot of features, have a chip that basically deals with all of these combinations and switching and multiplexing and everything. So you can connect almost anything to any set of pins on the cable. And the way that works is that Actually, let me just open up our wiki page. And I can show you. So basically, there's a custom vendor-specific protocol that runs over these CC lines. So if you go back to the cable, just show you what's going on here. Oops. Where were the pins? I need to bookmark these pages with the pins. No, I don't know where that page was anymore. But anyway, you can never remember where these things are. Is it here? Oh, the introduction section. Okay. Yeah, so here you can see, by the way, this is the one I was showing before. This is supposed to be the plug side, but then the device side does have this D plus D minus thing, and they call CC and VCon CC1 and CC2 because remember, this can be flipped over, right? So either is going to become CC, and then the other one is going to become VCon. So the devices are going to have a chip that that basically deals with with figuring out which way the connector is flipped and sending all the signals to the right place. And so on the CC line, there's a protocol called USB power delivery, which isn't for power delivery anymore. It's for a lot of other things. And this is like it's a whole different protocol, and some of it is insane because it is derived from a more insane version of this that used to run over their legacy USB connectors, and they stuck it on the VBus line because they couldn't stick it anywhere else. But basically, there's this whole protocol going on here, and there's this whole, sequence of messages you exchange. Like one side says something, and the other one replies, and there's timeout, and there's all these rules for how it's supposed to work. And this is how you can get all the fancy USB Type-C features, where a device figures out what's plugged into it, and if it's like a DisplayPort adapter or a Thunderbolt cable, and if you plug in two computers together, how they can figure out which one is supposed to be a host on the device if it's USB, or if it's going to end up like on DisplayPort or something. All of that is done by negotiating over this one little wire. And so Apple decided they were going to run their own custom thing over that because the standard has a provision for vendor-specific messages. And so basically, by sending messages to Apple devices over this wire, you can get it to give you extra features over the other pins. And so for serial on the Macs, we need to talk USB PD so that we can get it into the mode where it will give us a serial port on one of the other pins, on two of the other pins. And then we need a serial port at 1.2 volts, which is it's the voltage that these Macs use for the serial. But there's more things on these pins, so there's all of these options that we can get. And so one of the things you can do, which is very neat, is you can reboot the Macs by sending a message over this line, which is very convenient for development because you get a very fast test cycle. You don't have to hold down the power button or anything like that. But then there's at least three pin sets that we can configure on these things. And so one of them would be this D plus D minus pair in the middle here. The other one is the other D plus D minus pair, which is interesting because you can only use it when you have either a special cable that has both sets of wires plugged in or like a captive device with no actual cable. And then the third set is SVU1 and SVU2. And there seem to be two more pin sets, but I haven't seen anything that uses them. Presumably they're the high-speed lines. And so after those special actions that reboot the thing and put it into like a DFU mode or just reset, there's three like sort of commands that do that. Everything else is just mapping different set of signals onto different pins. So the one we care the most about is the debug UART, and this is a 1.2 volt serial port. But there's more things. We definitely want USB to work. That would go over one of the two D plus D minus pairs, and this is what I'm going to call DFU USB. But it's just a device C3, like it's a USB device mode basically. And the idea is that if we have a driver for this, the Mac will behave like a USB device, and then we can run, say, a serial port over that or something else, but it's going to be much faster than a normal serial port. So this, we definitely want to pass through this to the host. But there's more things. There's also an interesting debug USB feature, and we don't know what this is, but I want to at least have the ability of passing this through. And that can be on the same pins, or it can be on the other set of D plus, D minus pins. But then we also have two I2C buses, which are for the USB PD chips, and those run at 3.3 volts. And then there are three different sets we didn't figure out yet. One of them is probably another UART. The other one is 1.2 volts, and it looks like another UART that we don't know what it is yet. And then one seems to have pull-ups to 1.2 volts, and I'm guessing this is SWD. So we're going to call this miscellaneous 1.2 volts IOs. And there's also... there was also a GPIO thing, I think. No, that was just the I2C, I think. Yeah. So basically, we can sum this up as saying we need the ability to, if we want to be flexible about what we support, and also make this useful for other devices, we basically have three sets of pins: D plus D minus top, D plus D minus bottom, and SBU1 and SBU2. And so over those lines, in some combination, we want to be able to run USB 2, 1.2 volts, let's call it GPIO, 3.3 volts GPIO, and also 1.2 volts UART and 3.3 volts UART, as far as like sort of hardware support. So we're going to have some kind of microcontroller here, and I want to be able to use a hardware UART for these modes. And for I2C, it would be nice to use the internal I2C peripheral, but I'm not going to make that a hard requirement as to sort of, because we're going to have some restrictions as to where the pins map, and I don't want to complicate this too much. I'm happy saying that if we can get a GPIO on those pins, we can say we can do I2C with that. And same with SWD. This is not intended... by the way, SWD probably isn't going to be useful on retail Macs anyway, because it's locked down, and I don't think it can be unlocked by end users. But... even without this necessarily being sort of a high performance SWD interface, it would be good to at least have the option of doing something like SWD. So again, as long as we get some GPIOs on there that when we can bit bang to do something useful, I'm happy. So we have these different features we want on these sets of pins, and USB 2 needs to be available at least on these two D plus D minus sets. And then the SBU ones should have at least the GPI UART thing. So we don't think we need USB over these, because I don't think anything does that. And so one interesting thing is that, of course, the Macs have a specific TX-RX pin order for the UARTs. But now that we have this idea here, well, first of all, if you have a cable in line between the Mac and the device, then you're going to, if you use a standard cable, you're going to lose one of these D plus D minus sets. So if we want to use both, say, debug USB and DFU USB at once, then we need a special non-standard cable that has both of these. And those do exist. They're kind of expensive to buy. They're like $30. But I think that's okay. Like, if for people who want to use those two debug modes at the same time for some reason, they can go get the cable. And I'm going to see if I can find some manufacturer in China that will make these for cheaper for us. But for basic functionality, with a standard USB-C cable, you would get one USB mode and one sideband mode, which means you would get, say, DFU, USB, and serial, which is good enough. So that's about the cables. But if you look at other devices, once you have these features here, it's like, well, there's more devices that do serial port over USB Type-C. So, for example, on Pixel devices, you can get debug on... Oh, by the way, so we said for triggering this on Macs, we need a standard USB PD. So just a single CC line. But if you look at how, for example, some Pixel phones do serial ports, it turns out that what you need to do is you get RxD and TXD on the SBU lines. And then you also need, and what was that thing? Oh, apparently these don't need any resistors. So you just get, if you can get the serial port on the SBU lines, then you should be able to use this as a debug thing for Pixel phones, which is nice. And I should try that on my Pixel phone. I have one now, just to prove that it works. But then also, if you look at Chromebook devices, there's this SUSI cable thing going on that SparkFun sells, and the way that works is that they actually they do actually stick USB over the SBU lines. So we should also have USB over all three pin sets, and the polarity should be set so that this, well, actually, the polarity is going to flip depending on which way you flip the connectors. So I'm relatively happy with the idea that that if you're doing this for a Chromebook device, then the sort of the software might ask you to flip the connector around on the, again, this is a debug device, so I'm not worried if for example, if some features require you to plug in the connector one way and it doesn't work the other way, as long as there's some configuration that works. So that's this for the SBU lines. And then, interestingly, we need 2 resistors on the CC lines. Normally, you just have one. So in this case, if we can just add this one resistor somehow, we unlock the ability to use it as a SUSI cable, which is nice. Again, so I'm trying to basically see how how many features I can add by making little tiny changes like this. So that's for this. And then I also heard that there's a bunch of devices using the Cypress USB PD controller chips that do the same thing. They put a serial port on the SBU1 and SBU2 lines. And then also use some kind of vendor-specific commands. So I think we can cover those by saying, if we can have a variable voltage, I don't know what voltage they're running you are at, but if we can make this variable, then we can also support a lot of those devices, no matter what kind of UART they use. So this is kind of looking at these features, one of the things we're going to need either way is a USB PD interface chip. So these are the, let me just add some filters here. So for the USB PD interface, I'm going to be using the, I thought I opened that and I guess I didn't. Give me a second. Put it here. Yeah. So I'm going to be using this chip called the FUSB 302, which is a very simple and nice USB PD interface chip. You can bit bang USB PD, but you don't want to. Because the time modes are very tight, and to be compliant, you need a pretty annoying, you need a pretty strict spec on the voltages and the I diagrams and stuff. So it's a lot easier to use one of these things. And these are handy because they have a lot of different features. They will do the CC line switching for you. They can apply vCon to one of the CC lines. They can automatically detect which mode and pretend to be both a host and a device. And they can measure the voltages on the CC lines, and they can measure the voltage on VBus. Why do I want the FUSB 302B, by the way? I know we saw, what did they fix on that one? I know that the I2C addresses are different, but the one I'm using is the non-B, I think. As Rod just mentioned that is the one I was previously using as the non-B. Oh, more like newer standards. I'll take a look at this in a bit. But it's the same. It's the same package, I believe. So, yeah. So basically what I was thinking is, okay, that will give us our one pull resistor on one of the CC lines. Unfortunately, it won't give us this special mode for the SUSI cable. But I was thinking, okay, so this chip can connect one CC line to its internal. This current source is basically the pull-up resistor. So you can see here the different things you can connect to a single CC line. You can have a pull down, you can have a pull up, and then you can have the actual USB PD communications. You can use it to measure the line through a DAC, or you can connect it to VCon. And I was thinking, well, okay, if we have VCon, this is really just a connection straight to the line anyway, right? Like it's supposed to be you're supposed to put in a fixed connector voltage here, but nothing says you have to do that. So if I have in the cable an option where I can just, instead of connecting this to a fixed voltage, I can just have a resistor in here, then I can have one of these be one of the resistors on one of the CC lines, and then VCon be the other resistor on the other CC line. And then it should just work, right? So, that is a very easy way of implementing that. So if we use the FUSB 302, let's say we use the B. I need to go look into the details of exactly the differences anyway. But oh, by the way, this is intended to be always used powered. We're not like this is basically a debug tool. So this is going to be a board with two different USB Type-C connectors, one that goes upstream to a computer and one that goes downstream to the device. And so we're going to assume we always have power. But because this chip can emulate both a USB, like a source and a sink device, so like a device that provides power and a device that consumes power, we want to be able to support both modes to also make this a nice, sort of USB PD debug cable. So that said, another nice feature that Rod is also talking about here is that it would be very nice to be able to use this as a USB PD sniffer. Now, I thought about this, and I thought about sort of passing through USB PD to the host and sniffing on the way, and that doesn't really make any sense because you would want to sniff, sort of communications between two other devices. So what I'm thinking is, for USB PD sniffing, the chip can do it if we just plug in the CC line into, like, the target somehow. But I'm not going to have sniffing as a sort of, ready-made feature of the board, but rather, if you want to use it as a USB PD sniffer, what you would want to do is either get a USB-C breakout board and just manually jumper the lines over to the board, and you can use it like that. Or you could get a USB-C cable and cut it open and sort of, break out the CC line and tee it off to the board. So it's not going to be sort of a, ready in the box USB PD sniffer, but it's going to have the hardware and software support to do it as long as you wire it up separately to the target. And I think this is the most sort of reasonable way of doing this, because if I want to actually add like two USB-C connectors with proper pass-through and everything, that just complicates everything way too much. So we're going to do it like that. We're going to say that this can be used as a USB-C sniffer for free if you just connect it properly, but we're not going to give you the connectors to do it, without any manual wiring. So we have this chip, right? And it can do the regular communications. It can handle sync mode. It can handle source mode. It can handle the line switching. It can handle VCon. It can measure VBus, which is another thing that is nice to have, because if we are using this as a test device to, say, test the USB power supply, then we can, say, request a certain voltage and check that it's actually getting delivered. Yeah, exactly. Rod says about the high-speed lines. That's actually the main issue, is that if you try to have two different connectors, then you would have to wire the high-speed lines through, and there's other issues with that. And DRP toggling, yeah. So this is what the FSB 302 gives us. Now, extra things I want to have, since this is going to be a device that has a host connector, I want to be able to pass through these debug and USB things. So we're going to need a USB hub that is connected to both. There's going to be a microcontroller on the board to drive all of this, right? And there's a USB hub that is tailing off to the microcontroller and to the three D+, D-, top, bottom, and SBU options. So that means with a 4-port hub, which is the standard port count, we can have USB on all of these options. And that means that we need USB 2 switches so that we can switch between the hub side and, this GPIO or UART thing. So yeah, Rod is talking about the VBus pin. So when we're talking to the Macs in serial port mode, we need to be a source. So we need to be basically a USB host, which means we need to supply power to the Mac, even though it's not going to actually use that power if it's a Mac Mini. And that means we need to provide 5 volts. Now, if it's a Mac Mini, the power required is basically nothing. So for a Mac Mini, we can just pass through the 5 volts from the host, and that means we need a switch. I'm going to make this smaller now. But if we are emulating a proper USB PD host, or possibly this is something I need to test, this might be required if we are getting serial into one of the laptops, which actually would try to charge over VBus, and so like one of the questions is whether, for example, if I give it a standard 500 milliamp or 1.5 amp VBus, are they going to try to charge off of that, or will they not charge and just behave as a sort of simple sink in that case? That needs to be tested, because that determines whether you require external power when the upstream VBus is not enough to get a serial port on these laptops, or whether you don't. But either way, we need to support the use case where we want to provide VBus power. And so there needs to be an external VBus in connector where you could plug in 5 volts at least if you want to just do a standard power supply, or if you want to sort of extend this into a test platform for USB PD configurable power supplies, then we're not going to provide like an actual power supply on this board or anything like that, but at least there should be a VBus in connector and some sort of I2C or something, or some kind of pins that you can use to, let's say, if you wanted to implement an actual power supply, talk to the power supply so that this whole USB PD communications protocol can actually control the power supply and therefore what voltage you get in. So again, this is basically free, right? It's just we need to have some connector on the board. This is by the way, the reason why I'm doing this like this is that if you look up FUSB 302 breakout on the internet, and you would think people have already built these things, you get stuff like this. And like this is a USB 302 connected to a Type-C connector with the USB 2 lines passed through, and nothing else. And like there's like VBus. But like, where are the SBU lines? Where are the high-speed lines? Like, you have this board, and you're just throwing away all these pins that don't go anywhere. Or things like this. And this is like one that has an actual chip, I think, or something. Or there's one that has. Give me a second. My intercom is telling me that my Amazon thing arrived in the locker, but I haven't picked it up yet. Yeah, or you get things like this, right? And like this one has these 2 test points are the SBU lines, but it's still missing the high-speed lines. And so it's like, there's all these breakout designs that just throw away unused pins that it's just kind of sad, right? Because otherwise you could have used them. So for that reason, anything that I can at least make flexible enough so that other people can extend this into more useful applications, that's nice to have. So that's why I'm saying that I'm not going to source more than 5 volts from this board itself, but I want people to be able to stick in up to 20 volts into an input connector if they want to. Though that would require implementing the actual voltage switching on another board. So, so basically, we should have ideally 2 VBus switches. One that connects VBus from upstream, and one that connects VBus from the VBus in connector. Or it could be a jumper. So that's another big question about this design, is whether a lot of these selections are going to be made by jumpers or by sort of soft switches. And this is not completely decided yet. Yeah, so everything on the VBus bus needs to be 25 volt tolerant. So the FUSB 32 can measure and tolerate these voltages, so that should be fine. On the downstream side, by the way, I do not anticipate trying to pass through like 20 volts from upstream. In fact, we're not going to do USB PD negotiation on the upstream end. I am going to break out the CC line to a test point in case someone wants to mess around with that. But the idea is that the upstream end of this is basically going to behave as, from the host perspective, it's going to be a USB 3 hub. And what I mean by this is that the host on the upstream side is going to see a standard USB VBus load at least on paper, up to 500 milliamps. So if you want to abuse that, you can. USB 2.0 and USB 3.0. And so for USB 3.0, I'm just going to pass it through to the device side. And that way, if, say, you are using this to debug a Mac, then you don't just get this DFU USB 2 mode, you also get USB 3 mode. So with the right cable and in the fullest configuration, you could simultaneously have USB 3.0 high-speed device mode on the Mac, and a UART, and a USB 2.0 debug link, and the USB 2.0 debug device mode, though I'm not sure if they can actually do 3 and 2 at the same time. It probably can't, but you could reroute these pins to also do, instead, say, for example, one of the I2C buses, or SWD, even. So you could have some very nice combinations of things going on at the same time if we have all of this. Yeah, if we're sniffing, someone might have negotiated 20 volts. So the architecture that we end up with here, and I'm going to make ideally would draw a diagram, but I really don't want to start up Inkscape now, is we're going to have a USB host port that is going to have the USB 2.0 lines wired together, which is the standard for devices. It's going to have the USB 3.0 lines pass through to the target, maybe with jumpers, I'm not sure, or some kind of, at least I'm probably going to put some kind of cuttable links on the PCB, so if this is going to be a problem, you can cut them. But there's signal integrity issues if you try to use jumpers for this, so I should probably avoid jumpers. But I think a couple of resistors, or 0 ohm resistors, or like, sort of resistors with a cuttable link inside is probably going to be fine. Are you allowed to use USB 2 hub and 0.2 hub? Yes. So USB 2 and 3 hubs are basically separate devices. So from the point of view of the host, these are different buses, and it doesn't care which one has a hub and which one doesn't have a hub, or where anything is plugged in. Then we're going to have a USB hub, which has the following 4 ports. We're going to have a DFP to the microcontroller, DFP to the A switch, DFP to the SPU1, SPU2 switch, and the B switch. And SPU1 and 2, in this case, at least, I'm going to, on paper, try to do it on the pinout of the SUSI cable, which means SPU1 should be D+. Now, again, this is going to flip over if you flip over the connector anyway, so, but at least, like, on paper, I'm going to try and make the canonical not flipped state to be the correct one for the SUSI cable. Though actually, this shouldn't matter, because I bet it's going to fix that anyway, because this probably works. Oh, no, it only works in one port, one orientation. Okay, yeah. So it's the same thing with it's the same thing for them, that it only works one way, but that's fine. We can deal with that. Now, as I said, though, to do this, you're going to need a special cable, but that's okay. Most of the features of this board will work without a special cable. Yeah, don't get me started on USB 2 latency constraints over 5 meters, because like I have a VR headset that has like a 6 meter USB 2 cable, and it only works with like half of the PHYs on the other end, because HP were lazy about putting redrivers on both ends. So yeah, like I have to run it through a hub to make it work. But we're not going to use long cables for this. Like, this is a test device, so we're not going for like compliance with any particular standard so much as general usefulness with short cables and stuff like that. So like if you like, like the USB 3 lines are just going to go straight through. So if you plug in a 5 meter USB 3 cable on one end and a 5 meter USB 3 cable on the other end, that's not going to work, and that's fine. Like, don't do that. This isn't a complying testing. It's not a physical layer compliant testing device, nor is it intended to be, something that passes UP certification, but rather it's intended as a test tool and the logical, to some extent, the logical compliance testing device. So yeah, just don't use multimeter cables. That should be fine. So host port, USB hub. Then we have a microcontroller, and a priori, unless we have a really good reason to use something else, I'm going to make this some kind of STM32. With the built-in USB devices. And then we have the PD interface. And by the way, this is a Type-C, of course. And by the way, one point here is that because this is going to be a dumb USB 3 device, effectively, if you plug in a Type-C to Type A USB 3 cable, that's going to work fine and give you all the features. The only question is that depending on what's on the other end and how the SS pins are passed through, you might have to flip it around to get on the right SS pins because there's going to be no mux here. But again, because this is a test tool, I'm okay with telling people you have to flip the port over for some use cases. Some Chinese devices do this too, and it's really lame for like a normal consumer device that you have to try both ways. But again, for a test tool, I can deal with it. Yeah, I heard about the STM32 shortages. I've seen that they're in stock at like JLC and stuff for a lot of them. So if it becomes a problem, we can try to switch to something else. But as long as I can get prototype quantities for now, if sort of volume manufacturing, I don't know what volume this is going to be manufactured at anyway, but if that ends up being delayed to next year, that's not going to be a huge issue. Okay, yeah, so the Type-C device port is going to have USB 2.0 separate, USB 3.0 passed through to the host port, and then CCX lines to FUSB, and SBU1, SBU2 to MUX. And so we're going to have USB 2.0 compatible MUXes, one for each set of pins. And it doesn't mean you have to run USB 2.0 over them. It just means these are compatible with USB 2.0 signals, so they can be used for sending the signal over to the hub or to sending it to something else. And then behind these MUXes, I want to support these modes. So I want to, on all of these 3 pin sets, I want to be able to have a UART, TX, R. Well, first of all, I want to be able to have 2 different voltage levels. So we're going to have level shifters. So I want at least 2 different modes that are software controllable, because we might be able to mix modes. So there has to be a 3.3 volt mode that is probably going to be a pass through to the STM32. And at least a 1.2 volt mode, but it should be configurable. So we're going to call this a 1.2 volt to 3.3 volt mode through a level shifter. No Thunderbolt on these things. I mean, how would you support? I mean, you could try to pass it through to the host, but no. I mean, if you wanted to sniff the CC line of a Thunderbolt cable, you can just get a Thunderbolt cable and cut it open and take the CC line out and tee it off into this, and that's going to work fine. And you will be able to play games with the Thunderbolt drivers and watch the negotiation and all of that. That will work. But this is not intended to have any Thunderbolt support as a device itself. So that's a whole different story. So yeah, okay. So we have these 2 sort of voltage options. And by the way, the shifters are going to be not the transparent kind of crappy kind, but the ones with the proper direction line. So we're going to have an extra pin. Basically, one pin is going to become 2 pins on the STM side. And then behind these voltage selections, I want to be able to at least do UART with both TX and RX polarities, because I expect different devices to have different options for this. And also, if the cable is flipped over, you have to flip them for SBU1 and SBU2 because they cross over in the cable. And GPIO. And so my idea was, okay, we have this STM32. If you have an STM, like these things have I can get one of them with a lot of pins. And so if you look at some of these STM32, I'm going to have trouble finding the datasheet now, I might not. But basically, my idea is, usually you can map out these UART pins to, this is just a random one, by the way. You can map out these pins to many different, these features to many different pins, right? So you have stuff like this, like USART1, TX, and RX and map to PB6 and PB7. But you can also get USART3, some of these control, we're going to use these things, but there's like USART3, TX, and RX on these 2 lines. but also, TX and RX on these other two lines on port C. And then there's also 3 TX and RX on these other two lines on port D, and the USR2 is on these 5 and 6. And there's probably more USART1 somewhere else. On the where was this thing? It's PB. I think USART1 is probably more than one. Yeah, so those are also on PB, right? So, like, for example, USART1 is on at least 2 sets of pins. And USART2, if I don't mess that up, is also on TX and RX are on there, and also on these 2 sets of pins. And USART3 should also be on these 2 sets of pins. So my idea is, well, why don't I just bridge those pins? I take the 2 sets of pins that can do USART1, TX, and RX, and I connect them crossed over, so that depending on which set of pins I pick, then I can just switch over TX and RX. And then we have 3 USARTs, so those 3 can be for all of these 3 different pin sets. And that means that we could potentially have up to 3 UARTs at once if the device on the other end supports it. And use the hardware for all of them. So this is basically ideal, right? So because we have 3 UARTs and at least 2 different pin settings for each, then it means we can have up to 1 dedicated UART for each of the pin sets and use the pin settings to flip over TX and RX. Yes, I want to configure factory programming the STM over USB-C cable. So the idea is that these things have bootloaders that can do DFU. So I want this to be unbrickable, basically. So the USB 2.0, this is basically going to, from the point of view of the host, it's going to be a dumb USB 2.0 device behind a hub when you boot it up. So if I remember correctly, there should be, yes, like boot from, where's this thing? I forget if it's this one. Some of the STM32s have these things. It might not be in the datasheet, but just in the other in the sort of proper full documentation. But I'm not sure about there is that. Yeah, I know some of these have bootloaders anyway. They can boot off of VFU. So yeah, I don't want to pass through unmodified SBU1, SBU2 because I don't expect. I've sort of given up on the idea of this being useful as a pass-through device between the host and the device for Type-C features, only for playing USB. So, like, SBU1 and SBU2 on the host are just going to be on a header somewhere, just in case someone wants to do something with them. But they're not going to be passed through through this itself. And connected, there's going to be at least test points or headers for everything, so as to not remove options for people who want to hack on and modify the board and everything. But I'm not necessarily going to support, that built in as a feature. So let's give you UARTs, and then these are also GPIOs, and then we're going to need just another 6 GPIO pins for controlling the direction lines on the shifters. And that also means that we don't necessarily actually we can probably get away without even a multiplexer here, because well, actually no, we do need that to switch between the UARTs between the 2 modes. Sorry. So there's going to be at least another multiplexer here on the other end. Let me think about this for a second. Yeah, we need that. So we need another 3 muxes here. That or the muxes could be on either side, right? So this could be either 3 muxes that switch between direct and the muxers, or instead of having like 2 sort of A B dual throw muxes on this side, if we find muxes that can do 3 USB ports on one end or 4 USB pairs on one end, then we can just use 1 set of muxes for everything, right? So basically, each mux would switch between USB and 1.2 volt, the variable voltage mode, or the fixed 3.3 volt mode. So sniffing SVU1 2 would be useful for people to run TBT. What's the protocol over SVU1 and SVU2, the low speed stuff for TBT? Like, what kind of PHY does the low speed stuff use? As I don't know about the TBT stuff. So Rod's talking about sniffing not just the CC line for TBT, but also SVU1 and SVU2, and that's a good point. If that can be done with that, oh, it's a high speed UART type of thing. What's the voltage levels on it? But it's differential, right? Or no, it isn't. It's LSTX and RX, so it's not differential. Yeah, as long as it's anything below 3.3 volts, it should be fine. What's normal voltage for? If there's a lot of normal voltages. Rod says normal voltage is nothing special. I mean, is it 1.2 or 3.3 or what? Okay, 3.3. Yeah, then it's fine. Yeah, we should be able to do that. In that case, basically, when you want to tee off for sniffing a Thunderbolt wire, you tee off the CC line and the SPU lines. No problem. That's just for sniffing purposes. I'm assuming you're going to be using some kind of external, either handmade or sort of breakout pass-through board or something like that. And you can buy Type C pass-through breakouts in China, and I'm sure they violate all the electrical specs for Thunderbolt, but you might even get away with it if you're lucky. So, especially if you don't solder around the actual pin headers on those sides, so it doesn't become an actual stub. That'd be actually, I should try that. I have a Thunderbolt cable and a Thunderbolt device and some of those USB 3 pass-throughs. I haven't actually tested Thunderbolt at all yet, but I should try it with some PCIe card and then stick one of those things in series and see if it actually works. That's one of the things with these high-speed interfaces is that, like on paper, you need to be very careful with them, but then sometimes you can do some rather extreme abuse and they still kind of work. So we'll see. But yeah, okay. So this is kind of the story that I have, and so what do you think? Like, I think this makes sense. So the bill of material for this is not going to be too bad. We're basically talking 2 USB connectors, 1 USB hub, which is cheap, 1 STM32, which is basically cheap, the FUSB 302, another USB connector, some muxes, and then some kind of programmable power supply. And at this point, I'm inclined to do what Rod did. I would really want to make it variable like Glasgow has. But at this point, I'm inclined to do what Rod did and just have it be jumpers to select the voltage, because that makes life easier. And you could still do something bad by programming it into the switch in the wrong setting to use the 3.3 volt one. Oh, and by the way, I'm going to have at least basic protection resistors in series with everything, just like Glasgow. So it's going to be like at least 50 ohms or something in series with all the lines, just to make sure that we're not shorting something hard if you did something wrong. But and yeah, so Rod's asking if I can draw a diagram of the muxing. So yeah, okay, let's go into a little bit of drawing here, shall we? So basically, I could use KiCad for this, but it's gonna be a bit easier to just do some basic drawing here. So we basically have 3 pin sets, and each one of these is going to be 2 wires that we need to deal with. Yeah, I'm familiar with PCI Express abuse. It's quite resistant, especially the first 2 generations. Actually, let me just copy and paste this. So what we have is one set of lines coming into a mux, and we're going to have, a priori, let's say we have 3 sets coming out of here. I'm going to make this a little bit bigger to make it more understandable. So let's draw a little diagram here. So we're going to have one of these things for each of the 3 pin sets that we can have on the connector. So one of these is going to be SPU12. One of these is going to be D plus D minus on the A side of the connector, and one of them is going to be D plus D minus on the B side of the connector. And these are going to go into... Just copy and paste this. Life easier. Level shifters. Oh. And a bypass. Oh, sorry. Actually, yeah. Can I get it to like remember the... Yeah, just do it like this. So we have 3 shifters, and then these lines are going to just be merged onto that. Let's do a bit of a... You get the center of this to show up. Yep. Cool. I'm just going to copy and paste that again afterwards. And then these are going to go to the hub. So should probably make the document landscape later. So let's draw the STM32 here. And put these hub lines down here. I think I just broke that group, yeah. Just ungroup that. So what we have is make it a bit shorter here to make it more obvious that these are pairs. And so I don't have to move everything again. That's the hub. And here's our STM32. I can just copy and paste this. And then the shifter is also going to need direction control signals. So basically we'd have GPIOs for those things. And then, of course, from the hub, we would also have something coming off of the STM32 for the uplink. And then finally, because I said we would also be doing this swapped RxTX strip, actually, it's going to be like this. Which might be a little bit confusing, but hopefully you get the idea of what I'm trying to do here. So for example, on this case, what we would have is these would just be direction control outputs, and then these would be and again, these would be pins that have this as one of the modes, but they can do more things, right? So hopefully, for example, there will be, because I'll probably have spare pins anyway. Hopefully I can at least rig up the hardware I2C lines to like one of these sets, and that way have some options of using them. Anything I can just do by adding traces on the board is easy enough. Sorry, these are 3. But I2C is a problem through the shifter anyway. That will only work properly at 3.3 volts because you can't. You can bit bang I2 through the shifter, but you can't use the hardware I2 through the shifter because the shifter needs to know what the direction is for both lines. And so this goes to Type C. So let's just do a bit of the diagram of the whole thing, right? So we have Type C on this end here. Just going to copy and paste this. I'm just going to not draw the border for now. Actually, just make it a landscape. It's still too small. It's too late for now. We'll fix it later. So this is a Type C connector. And so these are D plus D minus B, D plus D minus A, SBU1, SBU2. And then on the other, well, we'll draw the other one afterwards. So some of them can do I2C. I need to double check on that. But again, that's more of a, best effort thing. Where's the pins here? Yeah, so for example, these are user 2 RxTX. Were they? Oh, is it the same thing? SPI is different from the USART. But we have. Oh, is it the same on these? No, yeah. So I2C1, for example, this one. So for example, I2C1 will map to USART1 TX and RX. So if that polarity, I can try to make it the same as on the Max, for example, and then you would be able to use these. And similarly, 2 is on the same as one of the USART3 TX and RX sets. And I don't know if we have any others. Is it just 2 I2C interfaces? Yeah, it's just 2. So it's worth getting the polarity of that one alternate set of... Wait, that's going to be the same anyway. Yeah, it doesn't matter, does it? Yeah, so no, sorry. What I mean is that it's worth getting the polarity on like if I2C, if SDA is here and SCL is here, then I want to make sure that like these 2 pins are routed in such a way that at least for the Max, those end up on the right pin set. And again, for SBU1 2, it flips when you flip the connector around anyway. So, so yeah, that would work in one orientation no matter what we do. So we definitely, that's one reason to put I2C on the SBU side, because that way, if there's I2C on the SBU side on the Mac, then you're guaranteed that, one of the 2 ways it's going to work. But yeah, like on the other one, on one of the D plus and D minus pairs, only one is going to make sense on the Mac. So for that one, I want to make sure that it's on the right way. And if another device has it a different way, whatever, you can always bit bang I2C at either of them. For pull-ups, well, the devices already have pull-ups because we're talking to I2C buses that already exist on the device. But it probably makes sense to, at least we're going to have pin headers for these things, right? So it probably makes sense to make it easy for the user to add pull-ups if they want to. But I don't think we need pull-ups for the Mac use case. And yet, it would make sense for I2C to be on the 3.3 volt pairs because the I2C is 3.3 volts, so that would work without the shifter. I2C behind the shifter is wasted, basically. That's never going to work. Yeah, unpopulated resistors is probably a good idea. So in this case, let's write this down here too. And actually, let's look up the, well, hold on first. Let me make these right side aligned. Don't know which one says the NSTL yet, but you get the idea. Again, a weird rogue group there, but... So here's our STM32. And then let me just finish writing down the rest of the Type-C connectors. So we're going to have our FUSB 302 in here. And so this is going to connect to both of the CC lines. Oh. And we're going to have VBus going through here. Yeah, so we need VCon in. And so what I'm thinking for VCon is that I'm going to have... What happened here? So for VCon in... what I'm going to do is make this configurable. And I think we can deal with just using jumpers for this. It's going to be one of three things, basically. And for VBus. For VCon, it's either going to be switched between... ...5 volts or... And this is like system 5 volt. This is like upstream 5 volts, right? Or some kind of pull-up resistor that I'm probably going to make configurable, like a an actual resistor you can mount, or some jumpers for a few common pull-up resistors. And so that's going to be the cheat for making a SSD cable. Basically, it's abusing VCon in as a second RP value. And then for VBus, there's going to be a switch. And so there's going to be a soft switch. There has to be a soft switch to make this work. Like a proper component switch. Just do it with just here. There we go. Should make this centered so that we can edit that more easily later. And then on the other end, I'm thinking that we will do another jumper option here. So we're going to have either system 5 volts or VBus in, which is going to be from some connector somewhere. And of course, there's going to be I2C from this to the STM32. Put this in here. And so this is, let's move this a little to the side. Basically, this is the VBus on these chips, by the way, on the FUSB is just a measurement input. It doesn't actually switch anything. So this means we can use the following modes. Yeah, the VBus switch needs to be able to tolerate 20 volts on this side, while this is still 5 volts. So that's going to be, we might end up with, well, one option would be to just say, if you want to use this as a sink, leave this jumper disconnected. But ideally, we want to not rely on people not forgetting to remove a jumper for this to not explode. However, since this is only used for driving, another thing we could do is just have a diode in here. And there would be some voltage drop here, but it would probably work for most applications. Yeah, we need to add the interrupt from the FUSB. Good point. Let's get that in here. I'll have to move the other thing afterwards, but this a bit. Again, this is all going to be, of course, more clear once it goes into KiCad. And actually, yeah, let me save this, by the way, before it dies. Because Inkscape is nice. Inkscape will save if it crashes. Like you do like a panic save to another file name, but only if you actually saved the file. If you've never saved it, it doesn't do that, and that really sucks. So, yeah, we got the interrupt, I2C, and for VCon we got those two options for jumpers, and then for VBus we got these two options, and the switch needs, let's just make a note here that it has to be either 20 volt tolerant or a diode. And then there's going to be some kind of, actually, instead of VBus in, I'm going to call this an AUX connector here. And so you can say this is basically for if you want to emulate a USB power supply. We can have an AUX connector, and then that will also have some kind of probably I2C or just GPIOs or something. It probably won't be the internal I2C, but this is definitely fine to do bit banging anyway. At least two GPIOs, let's just call it, at least two GPIOs for if you have an external power supply, something you can plug in here to control it. Yeah, we need a pin for the switch, of course. Let's see how I'm going to draw this. Can Move this a bit here. The layout is a bit annoying now, but I'll probably just remove this a bit higher anyway, and just be less messy that way. Yeah, something like that. Not the prettiest diagram ever, but yeah, it works. Some hubs compute USB to SRC natively? Oh, really? I didn't know that. Is that really useful, though? And the idea is that STM32 should be programmable via DFU mode anyway, so I don't think we care about that. Just fixing up these things. For recovery for triggering DFU mode, there probably is some boot mode thingy. I need to look at that. That's something to investigate. And then let me just finish drawing this out. So we got VBus, CC, SPU, D plus D minus, grounds are all implied. And finally, then we need another Type-C on the other end, which I'm going to draw smaller because we don't need the whole thing. But basically, it's going to be just this is going to supply system 5 volts. We're going to have actually, you know what? This doesn't even need to be this large because I'm going to put the other things down here. So something like that. And then the SS lines get passed through. I'm going to be lazy and just say everything is on those because I don't want to draw 4 lines for no reason. So those are all just passed through, and we can make that a little bit thicker to show that. And those will at least there will be some attempt at impedance control on those lines. At least I will do my best guess to keep that. Yeah, I'm not gonna characterize them, but at least I'm going to look at the board stack up and the spec from the manufacturer and design them in such a way that they keep the right impedance. So let me just read the chat for a little bit. Yeah, I hate pushing buttons when I need to do a lot of test cycles. But pushing buttons for recovery when something has gone horribly wrong is fine. So, but like for example, you can enter DFU mode from your existing firmware, right? So if you don't crash it, then it's fine to press a button. But yeah, if the hub has some magic like config request, you can send it to toggle the pin. That would be quite useful. So let's make a note here to investigate that. Yeah. About breaking out the boot pins to jumpers. Yeah, don't worry about that. Like, it's implied in all of this because I hate how all the other breakout boards don't do this. Like, any pin that has a useful function that is not being used is going to be broken out to some kind of jumper. Like, I think if I can get away with it, at least every single unused STM32 pin, if I can get away with it, will go to at least a test point that you can solder to. Unless I really run into space constraints. And definitely the boot stuff will be on jumpers, so don't worry about that. That's something that like that's the whole reason why I'm designing this and not just telling people to go get a breakout and wire an Arduino is because of that. Is because there's nothing good that doesn't require you to solder to some extent to use it. So yeah, don't worry about unused pins going to waste. They're at least going to be accessible somewhere. And yeah, so let's see if I can figure out about that. We can look at that in a second. Let me just finish this diagram. So we got D plus D minus A and B, which in this case are connected together because that's the correct thing to do when you're doing a simple USB to device on type C. And then for CC1, we would do the standard thing. So what was this? A pull down, whatever the value was. We just need a PD. RP. Actually, I should just draw an actual resistor. How many wiggles do you draw? I think this works. Ooh, that got really. What's the standard squiggle number for resistors? Also, I didn't do this right. There's got to be a standard for this, right? Three on either side sounds about. Well, some people do two. Huh. Interesting. But actually, I guess what we want is basically this, right? How did that end up? Okay. And it was RD, right? If I remember correctly. Yeah. And then nothing on the CC2, right? Nothing on VCon. It's just 2 of there's 3. Interesting. Also, I feel like this is backwards for some reason. Whatever. Why not KeyCat? Because this is not a schematic yet. This is a block diagram. Once we decide what all these parts are going to be, it's going to be KeyCat. But this is just an overview of the of what's going into this design. It's not an actual electrical schematic. That's why there's no grounds and no capacitors and no nothing. Yeah, the left fan port is going to be fixed to sync only. I'm declaring this to be a debug tool, and you're expected to plug in a host on the other end. The wire on the right, the visitor seems higher. No, it's not. It's the same. It's symmetrical. Yeah, so that's pretty much it does for the other Type-C. I guess I should probably draw this as an actual USB port on here. And I have the space anyway, so why not? Also, these things only do... well, we don't need that anyway. I think I just did something weird there. Okay. Yeah, the thing is, I was thinking about that, about it being a USB PD host. But the thing is, if you pass through, like, if it's a USB PD host, then what about VBus switching, right? Like, okay, then it switches VBus on, but then we need to switch VBus to the target, and then if we pass through CC, then if the target requests a voltage change, then our voltage changes, and like I thought about my original plan was to make this into a true pass-through that you could somehow debug PD stuff through. But then thinking about it, I don't think I want to do that. Like, it's there's too many corner cases. If you want to sniff PD from your host, then tee it off on this side. Otherwise, just yeah, like it feels like it's going to be complicated to actually use that way if you try to pass through PD and then also use it as an interface, because like the host might just kill your VBus at any time, and then the whole thing's dead, right? So yeah, for alternate mode in MITM, that'd be nice, but then like then you need two PD interfaces, right? Or some way of altering the responses. So I mean, you could do that by having like a daughter board that just gives you another FUSB 302 and things like that on the other end. But then you also run into timeout issues. Or what do you have in mind exactly for the MITM use case? Yeah, that's the thing, right? It's like if it's fine to like I'm gonna have enough test points and things in here so that if you want to build it into an MITM, you could by adding another FUSB daughter board and the external routing for that. But it's not going to be a built-in feature. I think it simplifies the way of thinking and the amount of things that can go wrong a lot if you just consider this left side to be a host access port for debugging, and you're expecting to always plug this into, first plug this into some kind of host that is sensible, and then this is the target port, and we don't try to pass through anything than VBus being supplied from here, optionally. I think that keeps the design quite reasonable. Which does not mean that you can plug both of these ends on the same host, right? You could totally plug this into the host as a debug port and then plug this into the host again and say this is now a device, an upstream-facing port, and you are now testing your own host's PD capabilities. or the other way around. You could even have the host try to supply itself with power, which I'm not sure what the actual power routing would think about that, but if it's happy to at least make the connection, then yeah, sure, you could totally do that and try to send here. Or you could give it external power here, plug this into a host, and plug this into the same host, and then charge your laptop and test. Yeah, like, yeah, there's a lot of nothing says they have to be different devices on either end. But role-wise, this is the debug port and this is the target port. I think simplifies things. And yeah, well, you could implement inject messages from here into an existing connection if we teed it off. But again, it's kind of like it's the same host. So if it goes wrong, it kills VBus and then it kills the debug connection. It doesn't feel. It might work for some use cases, but it doesn't quite feel like it's going to be easy to explain how to make that work. But that said, there is going to be a pin header on CC here, and there's no reason not to provide a pin header on the CC lines here and a jumper. So let's say that, and of course, SBU1 and SBU2 here will also be on pin headers. So let's say that if you wanted to really make this into a pass-through, you just wire a jumper wire across, and off you go. I think that. Do you think that would be perhaps useful enough? If I just make it like hand wireable into a pass-through mode for SBU1 and 2 and CC? Yeah, it could be on the mux, but that depends on whether if we end up using because I know there are 3-port and 4-port muxes, but this is going into part availability. So if we end up using 4-position muxes, then absolutely, though, at least for SBU, one of them will go upstream because it'd be dumb not to. But otherwise, it'll be a jumper wire. Yep. Presumably, you wouldn't really need to jumper VBus across, because as soon as VBus is applied here, the STM32 could boot and just turn on the switch and apply VBus downstream. So I think you could get away with just having the software part configured to do that. But yeah, you can still jumper it through a wire. I think that's also a good reason not to make that a strict jumper, is that if you short out this switch and you end up in UFP mode here and requesting 20 volts, you don't want to murder it by making the local supply 20 volts. So that's it sort of like, if you're going to use it as a pass-through, then I want you to actually wire a wire through as a sort of, implicit expression of intent that you know what you're doing. You mean jumper it and not connect it to anything else, but we need to supply this somehow, right? This needs 5 volts, so if we just jumper 5 volts VBus, then what's the M32 going to do? I mean, this needs 5 volts to run, right? Well, actually, there's going to be, to be fair, there's going to be a regulator here, so there's no reason why that won't take 200 volts on the input. So we'll try to make the power supply circuitry on this be perfectly capable of handling 20 volts on here for safety, and because why not? None of this is going to use a lot of power anyway, so even if it's just an LDO, I think we can deal with 20 volts in, 3.3 volts out. As long as you don't close this with 5 volts on this end, because then you'd be backfeeding whatever is on this end. No, to be fair, that will also work to the pass-through mode, right? Like, this is technically this, so pass-through mode would just be turning on the switch. That would work. Yeah. Because, I mean, we don't actually need 5 volts for anything here other than VCon in, I think. And we could have a little tiny LDO for that. Yeah, that would probably work. Well, we'll look into those details a bit later. But considering everything here is going to be on 3.3 anyway, except VCon in. Do we want to have an LDO just for VCon in? As long as the dropout is low enough that it doesn't matter. If it's the input is 5 volts, then we can probably get away with that. Yeah, I think that's doable for safety. Just have a little LDO here. So in that case, we're going to not call this 5 volts. We're going to call this VBus. Yeah, I mean, for the jump, what I mean is that, if we just define the local bus as not necessarily 5 volts, then we can get away without requiring a jumper, and it's safer anyway, because then we just design it with the assumption that it's not necessarily 5 volts. And in that case, that just means there's a little LDO here. And that is safer because this is a VCon option. So if we decouple that from VBus, it's safer anyway. Hold on. Let me see how I can route this. A little bit tight on space here. I'm going to redraw this a little bit. We'll just go center like that. I'm running into grid issues here. Whatever, close enough. Actually, I should also make these wider on that. Which option I picked? Was something like that anyway. And then we just put VBus on the other end here and call it a day. Let's go 5 volts. Something like that. Yeah, okay, so that makes a bit... I think that makes sense. We're going to call VBus a potentially 20-volt bus all the way through anyway. It should never happen from this end unless you're doing the jumpering thing, but we're going to allow for it. And the only thing that needs 5 volts in this whole design is VCon in, so we're going to put a little tiny 5-volt LDO here, and that's just going to pass through 5 volts if VBus has 5 volts, and for VCon that should be fine. And I think that's about it. And then, of course, the actual power supply for the board is just going to be, and 3.3 volt it'll be on. think that makes sense. And then, yeah, there's implied 3.3 volt supplies for everything. Yep. Cool. So I could take VCon from the UFP. I can't, because there's a cable in the way. And the cable is not going to pass through VCon, because cables don't do that. So yeah, I think this is pretty much it, and it's basically the design I had in mind. I'm happy with the little details we worked out here. Any other ideas? So basically, after this, the next step is part selection, and the big question marks are, well, what hub chip we use, though there's not that many options there. Something that has a GPI would be handy. Otherwise, it doesn't really matter. For the shifters, I'm thinking Rod's already come up with something. Which ones are you using? So are these the 1.2 volt support ones? S74 AVC 1T45D BVR? AVC 1T4. What was it? 1T45 DBVR. I typoed something there. SN. You can add for those things. .2 volt to 3.6 volt supply range. 4.6. Yeah, okay, so these are basically 3.3 volt versions of similar to the classical ones. It goes low. Says optimized for 1.4 to 3.6, but it'll go up to down to 1.2. And they're both cool. Yeah, that works. No problems with that. And the supplies for the shifters would come from a we're going to do the same thing you did. I think that's a reasonable solution, and it keeps it simple. So we're going to have a just call that LDO. It's kind of in their own direction, but I'm going to cheat and do it like that. Actually, it looks ugly, but I'm just going to, let's do it like this. Sure, assume that's understandable. And that would be driven from probably a 3.3 volt bus, because we don't want to risk it anywhere else. And that's that. And this is going to go basically some kind of jump purple settings thing like Rod did in his design. I'll probably just copy this whole thing. How did you do it? If you're okay with that. Yeah, this kind of thing, right? This, yeah, 1.2, 1.5, 1.3, 1.5, 3.3, that's pretty much the options we need. Just got a ping somewhere. Not sure where. And yeah, that looks good. So the questions here are, well, we already, I'm just going to use these shifters unless there's a good reason to change them. Yeah, no problem. I mean, I'll review it to make sure that it makes sense, but it's always good to start off with something someone else made and already thought about. So yeah, the same regular design. And by the way, it's only going to be a single LDO for everything here because we're switching between 3.3 volts and one fixed other voltage. I'm assuming we're not going to need two different voltages, like 2.5 or 1.2 or something like that. If you need that, then well, sorry, you only get to use one of them. But I think that's a reasonable trade-off. The Mac only needs 1.2 and 3.3, and I'm assuming that most of the devices are only going to use one voltage or not have that many options to choose from here. So just keeps it a little bit simpler. Since we already have shifters and the muxes for every port, and I don't want to get into like a giant, Uber anything to everything device. I'm like, the reason why this is very handy. This I'm using the port multiplexing on the estimator is handy because I can have a lot of options just like bridging pings together, which is cheap. But I don't want to have too many sort of per port chips. And yeah, that's good. Other things. So yeah, so the questions are what muxes, what hub, and that's pretty much, and what exact STM32. And also what switch for the VBus switch. That's pretty good. So I think instead of jumping into that right now, and also since I'm getting hungry, that I'll probably end this pretty soon, and then possibly start another stream later. I sit down and get a bit of part selection done. But also, I think it's good to have streams that are sort of self-contained and not 5 hours long, because I think there's a bigger chance people will actually watch those after they're over. So, yeah, if you have any other things to suggest about the design or questions, let me know. Otherwise, I think that was pretty good for at least this part of today. Someone mentions the Cypress chip that has GPIOs. Yeah, like if it's something that we can. Oh, to be fair, one cheat we can use is if it's a hub that has controllable VBus for downstream ports. That's one cheat you can use. Is use the VBus switch output for one of the other ports as the DFU trigger for the SC132. Sorry. As an MCU. Yeah, so there's this power switching thing, right? So it might make sense to just use this. Since it's not like we're going to actually be using power switching anyway. But because the power switching for the downstream ports is not going to be useful for anything like these things, we might be able to get away with using that as a DFE trigger. So that's going to need a little bit more of investigation, but basically this kind of thing, right? Power switch driver output. That could definitely be used as a boot mode abuse, as long as the default state, on is, as long as it's always on, even when there's no device connected, which it should, I think. Then we use that as the default state, and sorry, 1 second, and then we can turn it off via standard USB hub commands to switch to DFE mode. A hub that can do billboard. Do we need that? What do you have in mind for billboard? Let's see, from stuff, yeah. Oh, you mean for like just to show people more info about the device and that kind of stuff? I've never actually used Billboard. Like I never tried it. So I don't know what OSs do it with it these days, but that might be interesting. But I don't want to constrain the part choice here too much to like some particularly fancy hub. So this is going to be more along the lines of some of the more Jelly Bean hubs you can find. I just don't think I want to use as long as it's not what is the Genesis Logic. I've had bad experiences with Genesis Logic hubs. They like to die for no reason whatsoever. But something that that GLC PCB has would be useful. They actually search by part types in here. Anyway, I'll see if they have anything. I don't know what they call these anyway. Universal bus function. Interface. USB ICs, maybe? Oh yeah, there's the USB. It's hard to tell which of these are hubs, but there's some Cypress stuff in here. 65642, was it? What's the 32? That's a 2.0 interface? Yeah, it's just interface. It's not helpful that they don't actually give you the like anything here, really. As a controller. These are probably just controllers. Let me search for a very common hub. Hopefully they have it and it'll tell me what they call it. A GL850, that was definitely one of the common ones. LCS. So where do they have these? Under what? Product type USB? Oh, is that a separate category? I'm not sure how they categorize these things. This is somewhat confusing. This is somewhat confusing. How are they doing this? I just search for USB. Is that what it is? Just USB? Okay, yeah, I think that's what it is. They just categorize them under USB. So yeah, I'll have to go through and see what they have. This is not the most reasonable interface. Yeah, they have data sheet links, but I was trying to just get a Google result for the names faster than downloading data sheets for everything. But yeah, like a microchip one is probably fine. That looks like a USB 3 hub. That's probably a USB 3 hub or controller or something. Can I sort by stock? No, I can't. I don't know what that is. Definitely not a 4-board hub, though. Why don't you tell me what it is? Like, this is the dumbest thing ever. Like, give me the description and the, This might be a hub. No, that's a UART. And I see they have some muxes. These are probably only 2-port ones. So we could use these with a and then another switch behind them, probably. Yeah, 2 times SPDT. So that's one possible architecture which would work fine. Yeah, multiple TTs are fine, but we don't care for this application, I'm pretty sure, because I think almost anything you're likely to plug behind it is going to be USB 2.0 anyway. Yeah, LCSC was the other place. There we go. That's more useful. 2.0. Yeah, here we go. How many ports? That looks like probably 4 ports. What's the difference here? Oh, those have 3 ports. Interesting. Not enough for me, but nice to know. I assume these are 4. Yeah, 4. Okay, that makes sense. Yeah. And as long as a lot of no connects. So do these not have the... They have the air current sense. Yeah, they have the port power enables. Oh, I see. There's just no connects for the ones without the extra ports. That makes sense. Yeah. And I assume these do work the standard request to set the power pins high and low. So yeah, I'll have to go through this in detail to check that. Oh, interesting. Internal registers. Yeah, this is when messing with it as a device, which might be nice to connect it to the STM32 to be able to do things. Though we don't necessarily want to make, like, we want to make sure you can at least boot without that. Yeah, so like the default would be self-powered, basically 0, 0. Yeah, it's a self-powered or bus-powered. So bus-powered would be the one we want for this. Or EEPROM if you want to make it more configurable. But I'll if we use this, for example, I would have a footprint for an EEPROM and some straps so we can change this, but I would probably default to just using the defaults with no EEPROM, so we don't need that unless we want it. Yeah, we want a USB 2.0 hub. I don't want a USB 3 hub, so. But yeah, I mean, as long as... Oh, there's battery charging support. Cute. I did not know that. It's interesting. Not what I need, but interesting. Port swap. Interesting. Oh, you can swap the pins. Neat. And you can change the maps. Yeah. I don't think we need any of these fancy features, but it's... Actually, the port swap thing is quite interesting. This is probably something, especially for SBU1 and SBU2, that we would want. And that begs the question as to whether if... I think as long as SMBus still works after booting in the default configuration, then we're fine. I need to double check this in detail. Strap options. Yeah, this is kind of an interesting question. Is if you set it to default, you would think it would still work as like an SM bus device or something, because it'd be kind of silly not to support that. I mean, of course, if it's an EEPROM, you would expect it to only work in this mode, but huh. I see. So there's like this write protect thing going on. So you need to toggle that. Well, one way of fixing this, if it really doesn't respond in self-configured mode, is to have it start up in self-configured mode, but have the hub reset line be controllable from the STM32. So once the STM32 boots, it could reset the hub again into slave mode and then reconfigure it, and it would still work in DFU mode. The only question is that in that case, we couldn't trigger DFU mode if the STM32 messes up the hub config. Yeah, this needs testing. It's a little bit tricky. Yeah, nothing says that SMBus works in default configs, which is kind of sad. Yeah, this particular hub isn't the best solution for that SBU12 swap thing, if we wanted to support that properly. It'd be usable, just a little bit annoying. Yeah, we'll see. Maybe there's some other hub we can also use. It's really just these in LCSC though. Anyway, I mean, it might be fine. We don't necessarily. I mean, the SBU swap also happens when you flip the port anyway, so that's not necessarily a problem. It would just be kind of cute to be able to do it internally. But if the hub doesn't support switching those without a complete reset, that's not a nice option. Yeah. Anyway, okay. I think that's good enough for now, and I should be finding some food. So I will be back a bit later today, most likely. See if I can get some replies on the... we submitted the version 2 of the Linux bring up for the M1 to upstream. So, but there's a bunch of other things that need to be done and some feedback I already got. So I'll see if I can work on that a bit later, and then be back for a bit more of part selection and maybe even starting on the schematic. Thank you everyone for coming, and I'll see you later. Bye.